So I know during episode 2 I stated that I would put bonus content after the theme song played, but it ended up being a little longer than expected. My info dump ended up being a little longer when I went to edit. So I decided I would just make a bonus episode. And I don't even have a Patreon or anything, so this is like just bonus episode for everybody. Woohoo. But it's minimally edited. So forgive me my ums and uhs and my starts and restarts and any potential loopy perseverativeness. There we go. Got all the syllables in. That my ADHD brain might have gone through. So I do hope you find the information informative, maybe a little entertaining, and just enjoy the nice, fun info dump episode. Oh, and also, I decided to include, I made a cheesy little theme song for my podcast that I just sort of made up on my own and sang to myself. And I thought, why not make that my bonus episode theme song? Why not? So enjoy that too. Hopefully, you somewhat enjoy my goofiness. Okay, so I'm not going to lie. I kind of feel a little like Ferris Bueller at the end of Ferris Bueller's Day Off when he's like, what? The movie's over. Go home, right? To the camera. Remember that? Probably aging myself, but it's a good movie, younger people. You should see Ferris Bueller's Day Off. Anyway, welcome to the bonus content, my little neuroscience / physiology geeks. I'm pretty sure that's who you are, or the medical SLPs, I guess I should say. I feel like medical SLPs usually are the ones who really loved all this physiology stuff, which kind of makes sense as to why we go into medical stuff, right? Still useful to know if you work with kids and you work with schools and stuff, because you still see a lot of complex medical cases, particularly in the schools, but also in private practice, depending on what areas you happen to specialize in. So, welcome to my bonus content. Woohoo! All right. I actually added in 3 different things that I thought maybe just didn't quite fit in with the episode or perhaps were a little too info dumpy. So one is going to be those memory centers in the brain, talking about how we have different encoding rates, essentially, for the different areas that mitigate different types of memory, long-term memory, which is super interesting. If you work with cognitive patients, this might really help. It's kind of eye-opening stuff. And then I actually threw in a little bit about the cingulate gyrus and how it actually does connect to different motor plans than what comes from the primary motor cortex, the volitional motor cortex, essentially. I feel like in my SLP studies, we really focused on primary motor, but there is a theory that there is an emotional motor pathway, basically. So I threw in a little bit about that because I learned that in my systems neuroscience class as well. And then I also threw in just this, I recorded this little teeny section on the size of nerves and the size of what is the largest nerve in the body, basically. It's like a little trivia thing, and also a little trivia thing on why we have really poor pain localization when we're dealing with very large nerves. It's very, very brief. There's more detail I could go into if I actually dug up my class notes, but I didn't. So this is it. This is my info dump of stuff I learned in my my systems neuroscience class. I think I took it in 2015 at the University of Arizona. Enjoy, folks. And with very limited review, I will say. So caveat, grain of salt here, I guess, because double check me, I suppose, because it might not be. My memory is not infallible. It's good, but it's not totally infallible. All right. Hope you guys enjoy the bonus. And thanks for listening, geeky peeps. We could totally be friends. Love you guys. It's the trauma-informed SLP. The trauma-informed SLP. Promoting safety, empowerment, embracing diversity. The trauma-informed SLP. Yeah. Bonus content. So since I was bringing up things about emotional memory encoding really, really quickly, I thought I would do a little bonus content here, a little post theme song. I almost said post credits, like podcasts don't have credits, or at least mine doesn't. Anyway, but post, jeez, I can't even think right now, you guys. Okay. I thought I would give a little bit of bonus post, outro, post music content on memory centers in the brain. So not about trauma learning. I just think it's interesting stuff, especially for SLPs out there. If you guys work with cognitive stuff, this is just interesting stuff that I learned from a neuroscience class I took when I attempted a PhD briefly back in the mid-20 teens at University of Arizona. So I took a systems neuroscience class at the PhD level and learned some cool stuff. So here's some bonus content from that. I do not purport to have remembered this completely accurately. This is stuff that I remember from the class, and I have not looked over my notes from that class in a while. So if there's any inaccuracies, please forgive me. I'm literally just talking about stuff that I think I remember learning, basically. Woohoo, bonus. Here you go. What I remember learning from that class is that hippocampal amygdala learning, so like that emotional memory is like one of the fastest, okay? Hippocampus definitely encodes long-term memory in terms of semantic learning. That's where you get into like the mice and the maze and spatial cells and all that stuff that people won Nobel Prizes for. That happens in the hippocampus. That's what people were measuring there. I know that like linguistically, we theorize that we encode especially semantic meaning in lots of different areas. That's why we can bypass it with semantic feature analysis, essentially. You can kind of bypass one pathway and try and get to the word or the concept a different way, right? So it's not like memory centers are what store all of it. I think the current running thought neuroscience-wise is that memory centers, like the hippocampus, they're like the relay station that's going to pull the right files, basically. They're the ones who are like, ooh, to have that memory, we need to connect these things. We're going to make a pathway happen through these neurons. So it's not like the warehouse that stores the files. Does that make sense? That kind of happens around the brain a lot. But you need that structure to be able to access those files. Does that make sense? I guess. They're kind of like the... I don't know. I guess they're like the Google search engine. I don't know. Or the card catalog. I don't know exactly. I can't think of a good analogy for that. But yeah, essentially, like the hippocampus, if you're having a semantic memory, the hippocampus is like sending out the right information to get to the right places in your brain, essentially, when you're trying to recall something. So emotional learning, super fast. Semantic learning, it can happen pretty fast, but that's where you need a few repetitions of something, right, to try to remember it. Like if you're trying to memorize somebody's name, and if you're me, you need like a billion repetitions. I'm so bad at remembering names, you guys. And if you ever meet me in the future, I preemptively apologize if I don't remember your name and you've already met me before. I always remember stuff we talk about. I never remember names. It's like the worst. Anyway, it's something, I think it has something to do with my ADHD. I think my brain just thinks names aren't that important. It's details about people that's important. And I'm like, thanks, brain, for making that decision for myself, because the other person thinks names are important and I need to. Anyway, ongoing battle. I digress. Let's head back to memory centers. So that takes a bit, right? Semantic learning takes a bit of repetition. And then there's habitual learning. So when you get into procedural memory, from what I remember in my systems neuroscience class, once again, I'm mentioning it's a class and it's been a while since I studied this because I am leaving room for error here with what I'm telling you. But the basal ganglia, we always talk about that in terms of Parkinson's disease and motor, and we know a lot of motor about the basal ganglia. But the reality is the basal ganglia actually is connected to all the brain centers. So it has cognitive aspects to it. It has like sensory aspects. It has all these different aspects for the basal ganglia circuitry. The motor is the best studied one. So that's the one we learn about because we know it the best, basically. And we know it's about scaling like your movement and this and that, like what's important, whatever. Okay. And it's habitual learning stuff, right? Which becomes that issue. That's where like Parkinson treatment is more about making sure there's more of a volitional intention rather than it being a habit, right? Because the habit system is starting to break down. So habit, you've probably heard it takes, a month or so to develop a habit. You have to do it regularly. So if you're trying to encode like a long-term memory into like a procedural memory or a habit, the reason it takes a long time is because the basal ganglia actually is one of the slower encoding systems. So long-term memories like get encoded in the basal ganglia, but they don't really encode quickly. It takes a lot of repetition for the basal ganglia system circuitry to be like, oh, I guess this is important for me to like start to remember this, basically. So that's what's so interesting, right? It's kind of fascinating stuff that, yeah, which also makes a lot of sense if you think about the cognitive stuff we start to see in Parkinson and other, similar issues with basal ganglia. You start to see cognitive impairments, memory impairments, that sort of thing. And it's like interesting because we don't know much about the effect of a degradation of that circuitry on those domains. But it kind of makes sense that we see some of that because it does have circuitry that feeds into cognitive areas in the brain. And if it's in charge of what is essentially procedural or habitual, then yeah, breakdowns in that would definitely affect how somebody is reasoning or problem solving or, all that executive function and stuff would definitely be impacted by that. So that's just a theory. That's just like me hypothesizing out here in my little office here. So in my little podcast recording area. Whee! That's just me hypothesizing out here in my little podcast recording area and just sitting out into the ether. But this is your bonus content, a little bit of something on memory centers, but that's why we have the different areas of memory, and that's why we have these different domains of memory that then get encoded in different speeds at different rates. Hope you enjoy that, SLPs, especially the ones who work with cognitive stuff. It's kind of nifty to know about, right? So, yeah. And also, just try not to think of memory centers as being like, the Raiders of the Lost Ark warehouse where all the memories are stored. They're much more like a relay station. Like, okay, yeah, if you want that memory, then I know how to get to that. I'll put in the search terms and boom, we'll bring it up and there it is. That's really more what it's about as far as what we know. It's more about the connectivity and not so much about like a file system, if that helps at all, hopefully. The bonus, a content transition, yeah. Here's another kind of interesting thing about the cingulate. We know that in certain animal models, including with primates and things, that there are motor connections from the cingulate to there are connections from the cingulate that send out motor patterns and bypass the primary motor cortex, interestingly. And there's a hypothesis that still also exists in humans because if you've ever noticed, if you're working with stroke patients and they might have the unilateral hemiparesis, and then when they laugh, you might actually see more activation on that side of their face than if they're volitionally trying to smile, right? And that's because the volitional motor is coming from the primary motor cortex, which might have been affected by that stroke. But the cingulate connections, the more emotionally driven motor planning, might not have actually been impacted by it or not as heavily impacted by it. So that's kind of interesting little tidbit neuroscience-wise that it might help to explain certain phenomena we also see in the SLP world, such as with just people with disfluencies, that when there's automatic speech or more emotionally driven speech, they can become more fluent. In the voice world, there's spasmodic dysphonia, where if it's emotional vocalization, it's clear. And the spasmodic dysphonia seems to mainly be present with volitional voicing, right? So it is kind of interesting because these are all different things that converge to help suggest strongly that our emotional system has their own access to certain motor planning. Kind of cool, right? The bonus, a content transition, yeah. Little piece of trivia time. I said vagus is one of the largest nerves in your body. Little piece of trivia for everybody out there. The actual largest nerve in your body, the largest single nerve as far as at the cellular level, is the sciatic. That is the nerve, if you have had sciatic pain, you know what I'm talking about. It's that nerve that comes from your lower back and it actually goes all the way down your leg. So that's that one where if it gets a little pinched or a little impinged or something, you know, especially for women when you're pregnant. This tends to happen, right? Where you get the pain and it's like you might feel it in the back of your thigh, and then it might move down to like the back of your knee, and it might move up to your lower back in a little bit, and then maybe it'll be in your back of your calf at some point, right? And it's such a weird thing that you get that pain response, right? But that's because it's all the same nerve. So your brain's not actually great at localizing exactly where the pain is. Basically, it's just getting the message like this nerve is annoyed. And so you experience the pain. Like it can be kind of all the way down your leg, essentially, or even in your lower back. So, piece of trivia, that's the sciatic. Another fun piece of trivia about the vagus. Quick side note, guys. It is really large, right? And it does carry 80% of that information, including sympathetic in your torso about your gut. So, like pain response and stuff. This is also why we have really bad localization for pain in our torso. And as like, especially cis females, we know what it's like, where it's like you get pain in your lower abdomen and you're like, I don't know if this is my reproductive system that's causing me pain, or is it my digestive system? Like, who knows, right? Hard to localize. And that's because a lot of that information is going up essentially in the same nerve bundle, and it's, you know, it does get sort of filtered out as it goes up to the brain, but essentially you end up with really poor localization because it's kind of coming from the same source no matter where the pain happens to be. So fun little topics, little bonus side notes. Okay,